Alright, thanks for watching, and today we'll define the single most important concept in all of analysis, the concept of a supremum, which if you like you can think of as a general version of a maximum. And by the way, here we call it the supremum, in other books they call it the antisocial social clubum, but this is way cooler. Now, again, supremum is kind of a chill version of a maximum, so let me give you a little analogy. What does it mean to have the best grade? Suppose I tell you the following. You did not get the best grade in the class. What's your first reaction? Hey, who got a better grade than me? And that's precisely what a supremum is. Namely, if something is not a supremum, something else is bigger than it. So, definition. Again, let S be a non-empty a subset of R. So, and let M be an upper bound. So, upper bound I defined in the previous video of S, namely a number such that's always bigger than all the other elements in S. Then we say M is the soup of S, so no soup for you, if the following is true. And again, let me maybe illustrate this with a picture because it's so important. So, suppose you have your set S, and I'm saying M is kind of like the maximum of S, so M is here. What does that mean? It means whenever you pick a smaller number than M, let's say M1, so if for all M1 less than M, we can find, or there is, an element S1 in S that is bigger than M1. There is, again, is S1 in S such that S1 is bigger than M1. So, digest this definition a little bit. I know it's a very complicated definition, and in fact it took me at least a year to completely get it. But think again of it in terms of the analogy. What does that mean to get the best grade? It means as follows. If you did not get the best grade, so if M1 is strictly less than M, there is someone else who got a better grade than you. So there is S1 in your set that is bigger than M1. Or, in other words, sometimes, maybe that also helps, supremum is sometimes also called the least upper bound of S. So note, sup of S is called the least upper bound of S. So least as in smallest. Of S. Least as in as follows. So first of all, M is an upper bound. So in other words, forget about the word upper bound. What does it mean to be the least upper bound? It means as follows. In other words, what does it mean to be the smallest upper bound? If you have anything smaller, so if M1 is smaller than your least upper bound, then it cannot be an upper bound. In other words, there has to be an element that's bigger than M1. Because again, what does it mean for to be something to be an upper bound? It means everything is smaller than that number. So in particular, if M1 is not the least upper bound, it means there's something else in that set that's bigger than it. And as I said, it takes some while to get your mind wrapped up in this, but let me do a couple of examples. Again, to really illustrate this definition. So let's take the set S. The set S to be, let's see, just to make sure. Yes, the set minus infinity comma 4. Okay, and again, if you want, here's the picture. So this is the interval minus infinity comma 4. And I'm claiming that the maximum or the supremum of S is 4. So claim supremum of S is 4. Okay, and what do we have to show? First of all, 4 is an upper bound for S, so that's not a problem at all. And now we want to show the M1 business. So suppose you have some number that's smaller than 4. So suppose, and again, I also want to emphasize M1 doesn't have to be in your S, in S. So suppose M1 is less than or equal to 4, then what we have to find some number in your interval, so S1 has to be in S, that is bigger than M1. Then we want to find, I'll abbreviate it as WTF, so you want to find S1 in your set, and it's very important, such that S1 is bigger than your pretend upper bound. Again, what is this saying? So if you pick any number smaller than 4, let's say M1, and it says, aha, I'm the new upper bound, S1 says, oh no, you're not, because I'm bigger than you. Okay, but now what is S1? So important in analysis, if you want to find something, usually you construct it. Well, let S1 just be the midpoint of the two. So let S1 to simply be M1 plus 4 divided by 2. Again, the midpoint between M1 and 4. Then notice, on the one hand, by construction, S1 is in your interval. S1 is in minus infinity comma 4, so that's good. It's strictly less than 4, but also S1, again by construction, is strictly bigger than M1. But also S1 is strictly bigger than M1, again by construction. And that's why S1, that's why 4 is the supremum of your interval. Supremum of S is 4. And again, that is pretty amazing because remember, 4 is not the maximum of your set because it's not in it. So careful. Maximum of S isn't 4 because 4 is not in your set. However, what is true is that the sup is 4. In other words, the chill maximum in some sense, it's 4. That said, the good news is the supremum is a generalization of the maximum in the following sense. So let's do one more quick example. So let S be the interval 0, 1. So I'm claiming that in fact 1 is the supremum of S. Well, but this one, luckily it's a bit easier to show. So suppose, again, 1 is an upper bound, so that's not a problem. So suppose some number, it's strictly smaller than 1. What we want to find S1 in S that is bigger than that fake upper bound. M1. But that's very easy because remember 1 is in your set. So just choose S1 to be 1. So let S1 be 1, which is in your set. Well, then by definition, right, 1 is bigger than M1, then S1, which is 1, is bigger than M1. So in fact, S1 is bigger than your number M1. All right, this is all good. Last but not least, okay, why do we care about this? So, I mean, first of all, little fact, as I said, if max of S exists, then the sup is the max. But the question is, what makes the sup so important? Why do we torture you with that? Because it turns out there's something I like to call the fundamental theorem of analysis, or which is called the least upper bound theorem or least upper bound axiom, which simply says, more or less, even though the maximum doesn't always exist, the least upper bound always exists. So, one last thing to conclude this theorem. Again, the books takes this as an axiom, but it's actually something you can prove. So, again, least upper bound. Theorem. Okay. Then, suppose S, again, is a non-empty subset of the real numbers, and that is bounded above. Then S has a least upper bound. That is, sup exists. And we'll discuss it more in next time in another video. But what makes it amazing is, even though the maximum doesn't always exist, the sup always exists as long as it's bounded above. So, in other words, all that this theorem is saying is either supremum of S exists or the supremum is infinity. So it always exists as an extended real number. So that's why we really care about this, and we'll prove cool things next time. Alright, I hope you like this. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.